This is columns part 6. Our next step is to find the radius of gyration of the cross section of this compressed member that failed as part of the tail boom. Okay, before we can find the radius of gyration, we need to find the centroid line, which is where the center of gravity passes. And the way you find the center of gravity on this area is the same as finding the center of gravity on an airplane. You just pick out a point of reference. They usually either pick the nose cone tip or the firewall, the wall between the cockpit and the engine compartment. It doesn't matter where your reference point is. You can pick a reference point 1 mile away from here. It'll still work. But you just take the weight of every component on the airplane, like the nose cone. Let's say it weighs 2 pounds and it's 3 inches away from the tip. And the center of gravity of the nose cone would be 3 inches away from the reference point, the tip. You'd say that many pounds times 3 inches. You write it down. Weight of the propeller times it's 7 inches or whatever. Write that down. Keep adding all these weights times their distances from the reference point. And when you get everything on the airplane added up, you divide what you have by the weight of the total weight of the airplane, and that gives you your distance from your reference point to the center of gravity. So we'll do the same thing with our cross-sectional area here. Okay, so we'll use the bottom of the L as our reference line right along there. Okay, let's divide our L into 2 parts. So we're taking this area of our L and we're going to divide it up into 2 areas, this one and this one. This area is equal to this area. This area is equal to starting right there at that point, that area, not the whole thing, just that part. Doesn't matter how we do it, but this is the way we're doing it this time. So this area times the distance between our reference line will be down here at the bottom. Okay, and halfway up there, because for that little increment of area right there, it balances out with another increment of area there to be right there. There's always something somewhere that balances with something else somewhere to be just like having both of them right there. So we're going to take all this area times this distance between there and there, which is halfway between there and there, and we're going to add that to the area of all that times its distance halfway up between there and there. And then we'll take what we have and we add that area times that distance plus that area times that distance, and we'll divide the whole thing by the whole area, and we'll get the distance to our centroid line, the distance between that dotted line and our reference line. So we're going to take the area of all that times that distance plus the area of all that times that distance, add them together, divide it by the area of all that, and get that distance between the centroid and the reference line. So here's how we do it. The area of this is the height of that, which is 0.317 inches, times the thickness of that, which was 0.0414. So there we go. There's that. Okay. And times that distance, which is half of the height. So there it is, 0.317 over 2, plus the area of this one. The area of this one was the length from there to there minus the thickness of that. Okay, 0.185 minus the 0.0414 gives us 0.14365. Okay, that's the distance between there and there. That distance times that thickness, which was 0.0414. Okay, there we go. That distance times that thickness, 0.0414, times the distance between halfway up and the reference point, which is on the bottom, which is half of the thickness of that, which isn't much. It's only 41 thousandths, so that's going to be 20 thousandths. Okay, it's going to be this distance, 41 thousandths divided by 2. So here we have the math. Okay, and all of those, okay, that plus that equals the area of the whole L, which we determined earlier was 0.019 square inches. That area times the distance from our reference point to the centroid line equals that plus that. So our distance to the centroid line, let's see, our distance to the centroid line is what we get when we do all the math here. That times that times that plus that times that times that. And we set it equal to that, and then we divide all that by that. That gives us the distance to our centroid line, which is 0.115658 inches. Okay, so let's go ahead and write that right here. That number there, that 0.115658 inches, is that distance between the centroid line and our reference line at the bottom of the L. Okay, so that distance plus this distance, the 0.0742, will equal this distance, 0.317286. Okay, and we have our thickness here of 41 thousandths. So that thickness plus that distance, 0.074225538, will equal this distance from the reference line up to the centroid. And this distance here, let's see, yeah, this distance is that one. Did I get mixed up here? Let's see, that distance plus that distance equals that distance. That distance plus that distance equals that distance. And here we have the same old 0.185 going across there. So those are the dimensions. That's what we really wanted to find out, is how far our centroid line is from there. Now we'll use that information. That's our center of gravity line. We'll use that to determine where our radius of gyration is. Our next step in finding the radius of gyration is to find the moment of inertia of this area. As you can see, finding this radius of gyration is quite a complicated process, but doing all this math, it'll make you appreciate those tables in the engineering books that just tell you the radius of gyration of any given shape, any given cross section of a beam, but they don't tell it about this one, so we've got to figure it out. Anyway, our formula for moment of inertia, we know the little itsy bitsy teeny weeny about amount of moment of inertia, di, is equal to an itsy bitsy teeny weeny amount of area. Let's just draw us a little area right here. Okay, that is, let's call this distance y. This is going to vary because we're going to integrate all the way from this line up to here. And that little area is dA. So dI equals that little area, dA, which is that distance times that distance. Well, that distance is the thickness of our L, which was the 0.0414, 41 thousandths of an inch. And if this is y, well then we'll call that distance dy. So our little increment of area is the thickness, that distance across there, times dy. Okay, and let's find the contribution of the moment of inertia. The contribution from this particular part, the vertical part of the L that's above the centroid line. See how I've got it drawn there and got a centroid line drawn there? We'll call that I sub that, the contribution of that. Well, it's the integral of di, there's di, which is the integral of dA times r squared, but we're using y, we're calling it y, so let's just change that to y squared in this particular case. Okay, and we're integrating from here to here. Well, that distance is 0.201628112 inches from there to there. So we'll let our limits of integration be from 0 to that, 0.201 inches. Okay, so the integral of dAy squared, well, dA is that times dy, so let's replace that with that times dy. That's what we did there, times y squared. Well, the integral of all this, what's the integral of y squared dy? Well, these constants, they just carry right on down, but the integral of y squared dy is y cubed over 3. So we, instead of writing y squared, we have y cubed over 3 this time, with our same limits of integration from 0 to 0.2016 inches. So we take that number, we plug it in for y, we multiply it by itself, then we multiply it by itself again to get that number cubed, multiply it by that, divide it by 3, and we get that number. So that's the contribution of this part of the L. Now let's figure out the contribution of this part of the L. Okay, notice I've got it drawn below the dotted line there. Dotted lines are centroid line. Okay, it's the integral of all the little itsy bitsy di's between there and there, which is all the little itsy bitsy dA's between there and there, times the square of their distances between there and there. That one's there to there, that one's there to there. That distance squared, okay, y squared. Okay, and our limits of integration are from 0 to 0.115, because actually we're going to call this 0 and this the 0.115. We're going from here to there. See that 0.115658481 inch from the centroid line to the bottom of our L? Those are our limits of integration from there to there. So that's where those numbers come from. Do the same thing we did with the last one. dA is equal to the thickness times dy. So we put that in there, times y squared. Okay, the integral of that, y squared dy is y cubed over 3. Uh-oh. I didn't write that in here, did I? Let's throw us a little y cubed in there. Okay. So we plug that in for y. We multiply that by itself and then do it again to get y cubed. Multiply it by that, divide it by 3, and we get that number. Okay, so that's the contribution of that one. Now let's do the contribution of this bottom part from there to there. Okay, that was, remember it was 0.185 all the way from there, but it was only, forget what it was, 0.185 minus the thickness, 0.0414. Yeah, it was Yeah, it was 0.14365. That was